Part 3, this is for questions 21 to 30. Question 21, a reaction occurs when ammonium chloride is added to calcium hydroxide. What is the role of ammonium ions in this reaction? Now, when you warm a salt of ammonia with a strong alkali, ammonia is going to be produced, okay? So if we have ammonium chloride here, and then I warm it with calcium hydroxide, I'll get first of all ammonia as a gas given off. Then from there, I'll get now calcium chloride and then plus water. Okay, so what is the role of ammonium ions? Now in here we have ammonium ions, okay, but it becomes ammonia here. Now what do you see? These are 4 hydrogens and these are 3. That means they lose a proton in there. So they can lose a proton to a hydroxide that is in here in the calcium hydroxide. Okay, then you get this ammonia here and then plus what? The water. Okay, so this one donates a proton and this. So because it is donating a proton, that means this one acts as an acid. So what's the role of ammonium ions? Okay, it acts as an acid. It donates a proton to the OH ions and then to get this ammonia. Okay, the next question 22, elements Y and Z are both in period 3. Element Y has the smallest atomic radius in period 3. Okay, smallest atomic radius. Now when you look at period 3 elements, the outermost shell electrons are being added to the same shell, okay, as you move across the period. So that means that the nuclear charge is increasing, the shielding is constant, and therefore the nuclear attraction for the outermost electrons is going to be greater. So meaning as you go across the period, the atomic radius has to decrease. So if they say that element Y has the smallest atomic radius in period 3, okay, that one might be chlorine, okay, before we go to argon, because that one actually doesn't react. So there are, I expect Y to be chlorine, okay. There are only 2 elements in period 3 that have a lower melting point than Z. When we look at a graph of melting points, okay, of melting points here, I can have sodium has a high melting point, then magnesium is higher, then you find that aluminium is also of course higher than that of magnesium, then there is a shooting here for silicon, then you come back down, this will be for phosphorus, but phosphorus, because it is a non-metal, then its melting point is going to be below this one of what? Of sodium. You see that? These are metals, they have higher melting points. Then from here, we have sulfur. Remember, phosphorus is P4, okay? It has covalent bonds that can keep them as solids in there. And then we have sulfur, it is S8. It has this kind of structure here. It's like a W. You have a sulfur here, 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 and there, okay, S8. Now that one, because of many electrons and that complex structure, it is going to have a higher melting point compared to this one of phosphorus, okay. So I'll put this one a little bit higher than it. Then we shall go to chlorine. Chlorine exists as a gas, okay, the atomic molecule. Its melting point has to be even below that one of what? Phosphorus, because phosphorus here, you can see it is P4, so it is more complex than chlorine, so this one has to be below it. And then the next one is argon. Then argon also has to be, it is a monoatomic gas, so it has to be below that of chlorine. So we have argon, we have chlorine here, you have sulfur, you have phosphorus, you have silicon here, you have aluminium, you have magnesium here, and then you have sodium. So they say that there are only two elements in period 3 that have a lower melting point than Z. A lower melting point. So these are the two elements that have a lower melting point than phosphorus actually. Okay, the rest of the melting points are higher than that of what? Phosphorus. So the two elements we are talking about are chlorine and what? And argon. You see that? So that means Z is phosphorus. So Z here is phosphorus. Now they are saying which compound could be R. I mean, they say elements Y and Z. Y, chlorine, Z, phosphorus. You see that? React together to form compound R. So I look for phosphorus and chlorine. So it has to be this one here. You see? D. Question 23. 1 gram of each of 4 different compounds of group 2 elements are thermally decomposed. The residue in each decomposition is the oxide of group 2 element. The volume of the gas produced from each reaction is measured at room conditions. Which substance produces the greatest volume of gas? Now, when we look at these compounds here, there is a carbonate and then a nitrate. Okay, so for thermal decomposition of group 2 carbonates and nitrates, it increases down the group. Okay, as you go down the group, thermal decomposition increases. Thermal decomposition of group 2 carbonates and nitrates increases down the group. The reason to this one, we give it in A level, okay, because of the decreased ion polarization. You see that? Yeah, but that one you talk about it in A level. It is in chapter 19, which is called lattice energy. Now, what do we do here? Now, because when you go down the group, the thermal stability decreases. That means at room conditions here, we are going to have what we have here, strontium and calcium. So below the group, remember, I mean down the group, it is the thermal stability decreases. I mean increases. So if the thermal stability increases, that means those carbonates or nitrates for those elements in group 2 that are down in the group there, they are going to decompose so slowly. You get it? So at room temperature, they might even not decompose. You get it? So that means I have to do away with what? The strontium. Okay? Then I have to come to calcium. Now, when you look at calcium carbonate, you decompose it, you are going to get calcium oxide, then plus carbon dioxide. You see? And then calcium nitrate, when you decompose this one, you are going to get calcium oxide, then plus nitrogen dioxide, and then plus oxygen. You see? And I can put a 2 here to balance the nitrogen. Then oxygen becomes 6. And then here it is 4, then 5. Here we must get 1. So that means I can put a half here. Okay? That means the total volume of gas here is 2.5. Okay? The 2 here and then the 0.5. You see that? But then here, the total volume of gas is 1 mole. So 1 mole of a gas at room conditions occupies what? 24 liters or 24,000 cubic centimeters. So now you'll get 24,000, then times this one. Of course, this one is much more bigger than when you get this 24,000 here times 1 in cubic centimeters. So we see a bigger volume with the nitrate. You see that? So that means our answer has to be B. Question 24. Sulfur dioxide in the atmosphere can form acid rain. This occurs in 2 steps. Oxidation of sulfur dioxide to sulfur trioxide. Actually, we call this one catalytic oxidation of sulfur dioxide to sulfur trioxide by nitrogen dioxide. So you have nitrogen dioxide here, which reacts with sulfur dioxide, and then you get the sulfur trioxide here, then plus nitrogen monoxide. This one loses an oxygen, it gives to this. Okay, remember oxidation is gaining of oxygen, so this one has gained one more oxygen to have this one here, and then this one, because it has lost an oxygen, then it is reduced, so it is a redox reaction. And then from there, why do we call it a catalytic oxidation? This one that is produced here actually reacts with more oxygen in the atmosphere, okay, then to give us back the nitrogen dioxide. Okay, so in catalysis, you'll find that what is called the catalyst might appear to be consumed first, but then later it is regenerated. You see that? And then next, the formation of sulfuric acid will be, you get that sulfur trioxide, then we add a molecule of water, then you get the sulfuric acid. So they are telling us that which row, they're asking us to give a row that identifies the atmospheric catalyst for step 1, and that is nitrogen dioxide. So when you look around, it has to be nitrogen dioxide. Okay, then, and the reagent for step 2, we are seeing what? Water. So nitrogen dioxide and this one here, that means our answer is going to be a C. Simple as that. Question 25. Which statement about the mechanism of an SN1 reaction of a halogenoalkane is correct? SN1, it is nucleophilic substitution reaction, okay? And there is one species that is involved in the rate determining step, or in the slow step. So usually we see this one in halogenoalkanes. It has to be a tertiary halogenoalkane. Like for example, if I have this one here, there is maybe, I can say this is R1, maybe this is R2, and then we also have R3, and then I have X here, a halogen. It can be chlorine, bromine, iodine, okay? And then from here, you know that this one is partially positive, and then this one is partially negative, because these halogens are more electronegative compared to carbon, so they tend to pull bonding electrons towards themselves, so appearing to have received electrons, and then they become partially what? Negative. Then carbon appears to have lost what? Electrons, so that's why it is partially what? Positive. You see? Then from there, we can see that these alkyl groups here are, they have what we call the positive inductive effect, so they tend to donate electrons towards this carbon here, okay? So in doing so, this one can easily go off, so that's why we call it SN1. Like one species here is involved in this rate determining step in formation of the carbocation. So we shall have the R2 here, and this one here, you have the R1 and then the R3 here. They are all donating electrons towards this, so they try to stabilize it. So a tertiary carbocation is more stable, okay, than the secondary carbocation, and in turn more stable than the primary carbocation. You see that? So in primary carbocations, in primary halogenoalkanes, that one undergoes SN2, okay? SN2, because the stabilization here of the carbocation, of this carbon here, not the carbocation, okay, the carbocation is not so strong because it is done by one alkyl group, okay? I have one alkyl group here, maybe I have a hydrogen here, and then a hydrogen here. So this stabilization here is not so strong compared to this one here. So what happens, a nucleophile, let's say like an OH, okay, can easily come in and then donates the electrons to this, and then this one goes. So these are two species that we are seeing here that are involved in the rate determining step. So for that case, this one is called SN2. You see that? SN, then 2. This is SN1. Okay? So that is that. Now they are saying which statement about the mechanism of SN1 reaction of a halogenoalkane is correct. A nucleophile is substituted by an electrophile. Of course, that is wrong. One intermediate is formed from two reacting molecules. No, this one is SN1 actually. I mean SN2. Okay. One intermediate is formed from two. This is the intermediate, by the way, when the carbocation is fully formed. So we see it in SN2. Then the intermediate is stabilized by adjacent alkyl groups for SN1. Yes, they are here, like I've told you. So this seems to be the answer. Okay. Then part D, they are saying the intermediate is unchanged now. Question 26. The repeat unit of a polymer is shown. This one is actually coming from what we call addition polymerization. 3 statements about this polymer are listed. And of course, if it is coming from addition polymerization, then we should know that the monomers have to be alkenes. Okay. So 3 statements about this polymer are listed. Its disposal is hazardous because it produces toxic gases. Yes, when you burn this, you produce oxides of chlorine here. You see that? It will be toxic. And what else? Of course, we have carbon dioxide. It will be produced. But the mere fact that we also have chlorine in here, you are going to have toxic what? Gases produced there. Then, so this one is okay. So wherever there is 1, then I'll take it on. You see that? That means D has to be out. Then 2 different monomers are used to make this polymer. Let's check that out. They form these polymers when the bonds open, when the pi system opens up. Now, I will close it in. Okay? So I will go here, then close this one here, open this, close it here. The same thing you do here. Bring it here. So what are we going to have? We have a carbon here. There's a hydrogen and then a hydrogen here. Now there is a bond that is being formed here. So that's a double bond. Then we have carbon and then hydrogen here and then chlorine. Now this bond here has been broken up. Okay. So that means we are going to have another monomer. So there is carbon here. It has hydrogen. Then again hydrogen. Then there's a double bond. Carbon, then there is hydrogen, and then here we have OH. So this repeat unit is coming from 2 different what? Monomers. So they are saying 2 different monomers are used to make this polymer, and that is also correct. So 1 and 2 are correct. So we still give this one a tick. 1 and 2. Then the monomer for this polymer is 3-chlorobut2 but2 1 O. How does even this one look like? We have 1, 2, 3, 4. Okay, 1, 2, 3, 4. but2. We put the double bond there. So we have 1 ol. So if it is but2 then 1 ol. I can have the OH here. You see that? Then there is this. So this is 1, then 2, then 3 chloro. So the chlorine can be there. And then this will be CH and then CH3. So it will be like that. But we are seeing that this one is coming from 2 different monomers. This is not the monomer here. You see? So 3 is off. So wherever there is 3, I'm putting this one off. And then 1 only. So all of these ones will be off. And then our answer has to be A. You see that? 1 and 2. Question 27. Methanoic acid has acidic properties similar to those of other carboxylic acids. In addition, it can be oxidized by the same oxidizing agents that are capable of oxidizing aldehydes. The ones that are capable of oxidizing aldehydes, we have Fehling solution and then Tollene's reagent. You see that? Then they are saying which pair consists of 2 compounds that will give the same observations with Fehling's reagent. And we can see methanoic acid as an option in all of them. You see that? So we leave it. Now, for Fehling's solution, we only look for aldehydes. This one is a carboxylic acid. This one is an ester. this one here is a ketone, okay? And then this one here is an aldehyde. That means we are going to have our answer as a D, as simple as that. Then question 28, which row gives pentanenitrile as one product? So pentanenitrile, we are having a halogenoalkane. So it must be having 4 carbon atoms, such that when you add the cyanide, that is another carbon to give you now 5 of them to become pentanenitrile. Okay, so we look for 4. This is 1, 2, 3, 4. Yeah. But then, which reagents are we using here? When you are using, when you are producing this one here as a nucleophilic substitution reaction, the cyanide you are using here must be in ethanol. Okay, so we don't just hit with this one. Actually, when we are using this hydrogen cyanide here, we always use it with ketones and aldehydes, in other words, carbonyl compounds, and then we produce what we call hydroxynitriles. Okay, hydroxynitriles. So we are not having this one, but we are looking for ethanol as a solvent. Ethanol as a solvent. So we are here or here. But then the carbons must be 4 first. So if you have CH3, CH2, pardon me here, I think this one looks ugly, CH2, then CH2, those are 3. Then this is the 4th, Br. Then you have to put potassium or sodium cyanide in ethanol. Okay, in ethanol, and you heat, then you can have the substitution reaction here taking place. CH2, CH2, then Cn, like that. Okay, it's a substitution reaction. Now, CH3, CH2, CH2, CH2. This is the one here. That means our answer has to be a B here. You see? But this other one here is CH3, CH2, 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 CH2. Those are already 5. So you are going to get hexanitrile. You see that? So that is how we get it there. Question 29. An ester, this one here, is hydrolyzed in alkaline conditions. R prime and then R double prime are different alkyl groups. Which row identifies the 2 products? Now, when I have R prime, then carbon, there is a double bond here, and then O, then there is this R prime here. So we are going to break this one here. Okay, and if it is under alkaline conditions, first of all, when you break this one here, giving it water, this one will give us the carboxylic acid. So you will have this one here, like that, then OH, this one will take the OH, and then the hydrogen will go to this one here. Then you will have R2, then OH. So this is alcohol, and then this is a carboxylic acid. Okay, then after that, because this is done under alkaline conditions, the carboxylic acid here will then react with the what? The alkali. Okay, we then react with the alkali, like for example, if it is sodium, maybe hydroxide, then you will get this one here, or then Na, and then plus what? Water. You see? Now, because this one is a strong salt, it will dissolve in that water, and then you get this one as an ion. Okay, something like that. But sodium hydroxide is not going to react with the alcohol. It will just react with the carboxylic acid. Okay, that explanation we give it in A level. Okay, when we are looking at what we call phenol. Why is phenol? It's like the benzene ring here. It's just the benzene ring, then with an OH. It's an alcohol. Okay, but this one is acidic. It can react with the sodium hydroxide, but not this one. The explanation is done in what? In A level. Okay, now what else do we have here? They are saying product 1 it is not going to be a carboxylic acid because of the alkaline what? Conditions. Now that is how they are going to catch you in A. You are putting a carboxylic acid, yes, you know. Here, when you break it down, you're going to get a carboxylic acid and then an alcohol. But that one will be so if you are doing it under acidic what? Conditions, but these are alkaline conditions. Are we there? Then the next one will be now this one here. It reacts to give us the salt, which actually dissolves to give us this one, you see? And then the alcohol there. So that means our answer actually is supposed to be what? B. Question 30. Which compound cannot be oxidized by acidified potassium dichromate 6 solution but does react with sodium metal? Now, a ketone here cannot be oxidized by potassium dichromate, okay? And also, a tertiary alcohol cannot be oxidized by potassium dichromate. This one can be oxidized, this one can be oxidized. This one will give us first an aldehyde and then later carboxylic acid. Then this one will give us a ketone. You see that? So that means our answers have to be off here, a C and D. So we have to look here. Okay, these two cannot be oxidized by this oxidizing agent. But then they are saying one of these ones here, it reacts with a sodium metal. That is an alcohol. Okay, this 2-methyl, it is called 2-methyl propan 2O, or methyl propan 2O. Because how does the structure look like? There is a CH3 here, there's a CH3 here, and there is another CH3 here, then OH. So the methyl is on this one here, you see? So 2-methyl propan 2O, you see? Then after that, this one can react with any alcohol, can react with a sodium metal to produce hydrogen gas. So we shall have CH3, 2 here, then C, then O, and then plus a hydrogen here as a gas. You see? So the answer therefore has to be A.